before we take our break, okay? As I said, intensive thinking comes from thermodynamics, the science of the circulation of energy. And it basically has to do with the basic concept of fuel. As everybody here knows, every single piece of technological machinery needs fuel. Whether it is the gas that you put in the gas tank of your car, whether it is the batteries that you put in your electrical appliances, whether it's the lithium batteries that you need to recharge on your iPhone or your iPod, we know that we need batteries for everything. So intensive thinking is simply a way of reminding you that just like our technological devices need fuel, one, whether it is in the form of oil or in the form of electricity or any process, any morphogenetic process needs fuel. And that comes from intensive differences. Hence the word that appealed to Deleuze. Let me first define the word intensive before we get to that. When you open a book of thermodynamics, a textbook, you're going to find a distinction between two different types of properties. The first type they call extensive properties, and they include length, area, volume, and many others. Number of components, amount of energy, amount of entropy, but these are the three better known ones. And then you're going to find a definition of intensive properties. Which includes speed, temperature, pressure, density, concentration, how salty the water is, how much salt is concentrated on it, and many others. Now, when they give you the textbook definition, and I'm going to give it to you now, it's okay. It establishes one difference, but this is where a philosopher needs to come in to really find what's significant about this. The textbook definition goes like this. Extensive properties are easy to divide spatially, whereas intensive properties cannot be divided. Let me give you an example. Imagine that you have a wooden ruler that's 1 meter long, and that has a length, an extensive property. And you divide it into two parts, you cut it. So now you end up with two half rulers, each one of which is half a meter long. So areas, lengths, volumes can be divided. That's what in a way architects do. Architects are given an empty plot, an empty volume of space, and now they're going to come in and subdivide it in different ways. Subdivided to create different rooms, subdivided to create different little niches for conversations depending on the type of building that you're creating, right? And you're dividing it both in this direction and in that direction, in different floors. And in a way, architecture is the art of artistic or creative subdivision of extensive properties. Intensive properties, on the other hand, and this is the textbook definition, cannot be divided. Think, for instance, that you had a gallon of water in a container, and say that you took a thermometer, you put it in, and you make sure that that gallon of water is at 90 degrees centigrade. I'm just making that up, right? And now you divide that gallon of water into two half gallons. Well, the extensive property, volume, does divide. Now you have two half gallons. But when you use your thermometer to measure the water in each of the two containers, it's not going to be 45 degrees each, right? If you began with 90 degrees temperature, you would say, well, you divide it into two, each one is going to be 45 degrees of temperature, but that's not going to be true. When you subdivide it, you're going to find that each one is still 90 degrees of temperature. Temperature doesn't get subdivided in space. Neither does pressure, neither does speed, neither does density, neither does concentration. That is the standard textbook definition. Deleuze, however, he mentions the definition, but then he goes beyond that. He says, there's more to this than just that. That may be the definition that makes a thermodynamicist happy, but that is not a definition that makes a philosopher happy. And so he adds two more philosophical aspects to this. Number one, intensive differences, and notice the word difference again here, drive flows or drive processes. Flow being one type of process, a process of movement, but intensive differences drive all kinds of different processes. In other words, intensive differences are fuel. Let me give you an example. I'm going to draw two maps of the Earth. That was supposed to be a circle, by the way. Now here I'm going to draw a map of the Earth using extensive properties, areas, lengths, and so on. Now, since I cannot really draw very well, I'm going to draw Mexico, which is really the only country that matters. That's Central America, that's South America, then you go over here, you find Florida, and then the rest of the United States, right? That is an extensive map. It's in terms of the lengths of coastlines, the areas occupied by different countries, the volumes of airspace that country considers part of their sovereignty. All extensive. And as extensive properties, they are essentially divisible. That is why we can make frontiers. Right? So the Mexican frontier today is right there. Of course, everybody knows that our frontier used to be all the way over here before somebody stole half of our territory. But let bygones be bygones. We're taking it back anyway. So that's our frontiers. Our frontiers are crucial, of course, in geopolitics. Frontiers are divisions of extensive properties. A map with intensive properties would look entirely different. And first of all, it would have to be animated. But it's a familiar map too. It's the map that you see in your meteorological forecast every day. You would, in that forecast, you would say, somebody say, there's a zone of high pressure, and then there's a zone of low pressure. That's an intensive difference already. There's a warm front moving west. There's a cold front moving east. So this is hot, cold. There's a slow mass of air moving near the Earth. There's a very fast mass of air moving on top of it. I'm not even going to draw that, but it's slow versus fast. Whenever you find intensive differences produce movement. Let me give you a simpler example. And let's imagine again something simple like a box, sealed box divided into two airtight containers with a little door between the two containers. And let's say that you fill one of the two halves with hot air and the other half with cold air. As you have it, you have an intensive difference there, right? Cold and hot. And in fact, you have what is basically a battery, a very cheap and very primitive type of battery, but you can use it to run your devices. All you need to do is open the little door between the two containers, and the hot air will spontaneously move towards the cold air chamber. There will be a spontaneous flow, and you can tap into the energy, into the motion energy of that spontaneous flow to run, say, a small electrical motor. Now, nobody would actually do that unless you're like stranded in an island with Gilligan and the professor just drowned or something, and you need to do something like that. But it shows you that an intensive difference is the most basic form of fuel. By putting two intensive quantities that are opposed to each other, and then putting them into contact, you create something that can drive a process. Now, since we are interested here in morphogenetic processes, processes that generate form, the very first question that intensive thinking forces you to ask is, where does that process get its fuel? Right? In the previous example of population thinking, I showed you where the process gets its fuel. It gets it from the sun. If there was no sun, then photosynthesis would not be able to fix that electromagnetic energy into chemical sugars, and then the whole chain of alimentary relations would not get started. So when I talked about population thinking, I brought a little bit of intensive thinking there, because you always need to account for what fuels a process. Processes don't just run on their own, vapors, right? They need an intensive difference. And intensive differences are always mobile. When you see this map, you need to see it animated. You need to see this area of a high pressure moving, the area of low pressure moving, the cold front moving, the hot front, the warm front moving. And it is from those movements and those interactions that everything in the atmosphere that there are creatures that we give names to are born. Hurricanes, thunderstorms, tornadoes, monsoon rains, cloud formations. The morphogenesis of the sky, which we as earthlings are very lucky to have skies that are constantly changing, and unless we have become so jaded that you cannot admire a sunset anymore, you're still kind of going every single evening, wow, this is different than yesterday, and it's a different painting than was the day before. Well, those paintings are produced morphogenetically, and they are produced morphogenetically using fuel. Where does the fuel come from? Still, it comes from the sun, because the sun warms half the planet and leaves the other half cold, and it creates a very basic intensive difference, out of which all the intensive differences follow. As I said before, it was by shrinking this system of differences that the steam engine was invented. The steam engine is just that. It's just a boiler on one side, which is the hot side. There is the earth on the other side, which is the cold side. And then there is a wire or something that connects the two. The moment you connect the two, there will be a flow of energy, a flow of heat going from one side to the other. Now, of course, if you just do that, then you're not going to be able to do anything. But if you then plug in a system of pistons in the middle of the wire, then they can take that energy, convert it into mechanical energy, and bingo, you have something that can, hammer leather or hammer, nails into things, or do whatever, all the different things that motors are used to do, drive wheels for a locomotive. And it is basically just a shrinking of the same processes that occur naturally on our atmosphere continuously. Now, just to end this little section, this is basically the definition of a body without organs. A body is called a body because, of course, a bounded body of water and air. This is floating in the middle of space, but it's bounded, right? You can see it from far away. So it's a body. And it's a body that's alive with intensive differences, constantly producing Hurricane Freddy, then Hurricane Susan, then Hurricane this, and we give them names because they're entities that last long enough for us to track, and of course because of the destructive power that we need to track them, but it is an entity that's constantly spawning things. Thunderstorms, with their expressive lightning and thunder, right? That many primitive cultures used to think is the angry gods talking to you. Because to this day, lightning and thunder are expressive, right? Depending on where you are, you can be fascinated, awed, or scared. But thunderstorms are expressive entities with a very specific architecture and move very fast maintaining that architecture. And moreover, some thunderstorms, in addition to the lightning and thunder, can spawn tornadoes if they have enough circulating air in the lower part. And those tornadoes can also last an hour, half an hour, and so on, while they do the destructive thing if they happen to interact with human settlements. And so it is a world, the atmosphere, hydrosphere, filled with creatures. The Mississippi, the Missouri River, the Amazon River, we give them names because they last in time and they have behaviors and they have moods, right? The Mississippi is angry today. Then, you know, we need to reinforce the levees because it's angry. Now, that's a metaphor, but it's also not a metaphor because you're talking about the amount of turbulence in that flow. And therefore the capacity of the river to overrun your defenses, right? And so the atmosphere hydrosphere is alive, but it's alive with a non-organic life. It doesn't have DNA, it doesn't reproduce itself, it doesn't have evolution. So it is a body without organs. It is a bounded body of water and air, animated by mobile intensities, by mobile differences in intensity, that can give rise morphogenetically to a variety of creatures, right? Some of which are dangerous, that is, some of which have the capacity to affect us negatively, some of which have the capacity to affect us positively, like a cloud formation during the sunset, which has the capacity to affect us aesthetically. But they have capacities to affect us. This is clear. Intensive differences drive flows. Remember, this is something that it is common knowledge. When you buy a battery, you know, a Duracell battery for your, you know, electrical appliance, it is a commodity-sized intensive difference. It is a chemical intensive difference in terms of the concentration of certain metals and certain substances. A typical battery is a sandwich of different substances, and so it's a chemical intensive difference, but it's an intensive difference. Just about anything that we use as fuel today is an intensive difference. And intensive differences are everywhere. They are in our bodies. This is what drives many of the processes in our bodies. They are in our industries. They are in nature out there. So for every morphogenetic process that you can think of, the very first question that you need to think about is, what is driving that process? What is fueling that process? But also think about the fact that the word difference is here. Again, considering that Deleuze is the philosopher of difference, right? Difference and repetition. Clearly, he was drawn to intensive differences because they are not just external differences, like the difference between this and this, which is just a difference in a kind of external, doesn't do anything. An intensive difference is a productive differences. Is the kind of differences that are there at the root of morphogenesis. So clearly, just like he was very you know, into Darwin for stressing the role of variation, of heterogeneity in driving evolution, he is very interested in thermodynamics for the role that intensive differences play in driving processes. And for the type of material, you know, the kind of body without organs that he talks about, which is, as when you read the definition of body without organs, is a bounded body of matter and energy animated from the inside by mobile intensities. Deleuze, early on, in Difference and Repetition, it gets rid of the term intensive difference and simply talks about intensities, because he says every intensity is a difference. So to talk about intensive differences is redundant. I mentioned yesterday how sometimes I disagree with Deleuze in the way he shrinks words, you know, how he shrinks capacities to affect and be affected to affects. I think that is confusing, just confuses people. And how much, you know, how many seconds are you shaving off your discourse by going from capacities to be affected, capacities to affect and be affected, that's pretty fast, to affects. Yes, it's a couple of seconds faster, but for you, for the audience, who's going to have to try to digest this, it's going to be a couple of hours of waste. So he does the same thing with everything. He shrinks and condenses. It's almost as if you wrote with this undifferentiated, almost like with eggs. Every paragraph was an egg. He's expecting us to unfold every egg into a reptile, every egg into a chicken, every egg into an animal. You know, by bringing a bunch of resources ourselves and then unfolding his paragraphs. And I love that idea because obviously to write with eggs, to write with bodies without organs, right? It's a new style of writing. And then it forces the reader to bring a lot of himself or herself to actually make those organs develop and make that meaning come out of that paragraph. But my question is, how many readers can do that? Of 90% of the readers of Deleuze are not capable of unfolding those paragraphs like that. Now, Deleuze might have thought, well, if we had to wait 400 years or 300 years to understand Spinoza, they can wait 300 years to understand me. No, we can't. No, we can't. There's like global warming coming on. There's like nuclear warfare. We have like 20 minutes now. Not 400 years, right? So my style has been to always just write about Deleuze fully unfolded. I'm not trying to count on the reader to unfold it any farther. But I can understand how he does it. And so when you read Deleuze, you're never going to, with exception a couple of times in difference and repetition, you're not going to find the phrase intensive differences, just like you're not going to find capacities to affect and be affected. You're going to find affect, you're going to find intensity. But now I'm telling you, intensity means intensive difference. I can even give you the page number where he says that if you write me an email. So he wants us to start thinking in terms of intensities as opposed to extensities. You will see tonight after lunch when we start talking about subjectivity, how Deleuze wrote his very first book on Hume, because of course Hume and Kant are even today are two main sources of theories of subjectivity. There's all kinds of other theories of subjectivity. There's Freud, there's Piaget, there's psychological theories of subjectivity, but from a philosophical point of view, the two main philosophers are Kant and Hume, and as we will see tonight, Hume is all about intensities. Now, not this type of intensities, but felt intensities. Not the temperature of the air, but the temperature as I feel it. Not the humidity in the air, but the oppressive humidity as I feel it. Not the pressure of water, but the pressure that I feel as a scuba diver, and I get deeper and deeper and I feel the pressure. And of course the intensities of color, intensities of aroma, intensities of flavor, intensities of texture. So we will be talking about intensities, subjective intensities tonight. Right? But I needed to present objective intensities first, because they were here before we were here. This intensive difference have been driving processes all the way till the beginning of the Big Bang. In fact, that is how the universe was born. Out of successive, and this comes to our second point, intensive properties exhibit critical thresholds. Oy. That word is thresholds. Critical thresholds, critical points of intensity at which something morphogenetic happens. The typical example of this is, of course, a line of temperature values, in which this is 100 degrees centigrade, this is 0 degrees centigrade, and we're going to be talking about the substance water. This is, of course, temperature. Now, everybody knows, and I mentioned it yesterday, that there are many points here, 99, 98, 97, 89, 85, and so on, which are entirely ordinary, in the sense that nothing happens at 80 degrees of temperature. Liquid water stays liquid, right? Nothing happens at minus 10 degrees centigrade. Ice stays ice. Nothing happens at 120 degrees centigrade. Vapor stays vapor. However, at those specific singularities, remember what the word singular means. Singular means special, remarkable. Something remarkable happens, something morphogenetic. Water, which is a type of architecture, liquid architecture, becomes solid, right? And so we go from liquid to solid to gas, which are three phases or three modes of organization in which water can exist. And they are always mediated by special, remarkable singularities, which are these singularities or critical points of intensity. Extensive properties don't have that characteristic. There are no critical lengths. Well, in fact, there are critical lengths, but always when associated with something intensive. But you can add, volumes, and you end up with a larger volume, and you keep adding it, and there is no real change from quantity to quality. Whereas here, at every one of those points, there is a change from quantity to quality. Right? This is something that Bergson, one of the main influences on Deleuze, stressed a lot. In other words, you change the quantity of temperature, 1 more degree, 1 more degree, and for a while nothing happens. If you are at 90 degrees temperature, and you change it quantitatively 1 more degree, you end up with 91 degrees temperature, nothing happens. That was just a quantitative change. But if you are at 99 degrees and you add 1 more degree, a change in quantity now has become a change in quality, because water now has become vapor. Right? This is, of course, also essential in the functioning of a steam engine. The steam engine is called a steam engine precisely because within the pistons, to be able to get to be able to tap into the energy flowing from the hot boiler to the cold earth, you need this phase changes of water, going from liquid to vapor and so on. Now these are very important because any change from quantity to quality gives rise to new qualities and is therefore morphogenetic. Changes from quantity to quality is what gives our world all its variety, all its interest. Now notice also that there are, let me reproduce this here, 100 degrees centigrade, 0 degrees centigrade. Options, even for the humblest substances. Water at 0 degrees temperature can become ice, or it can become snowflakes. Ice is a solid architecture that is relatively boring, right? You can make it less boring by creating ice sculptures, with a chainsaw or something like that. But an ice cube by itself, you examine it under a microscope, it's just a repetition of hexagonally shaped crystals, one after the other. There's repetition, but there's no difference. And so Deleuze considers ice because it involves repetition, the repetition of crystals, but it shows you this is the kind of repetition that it is unproductive, precisely because it doesn't have difference. But when you consider snowflakes, every snowflake is different than every other snowflake. They still have the hexagonal symmetry, where some of them have big dendrites, dendritic growths at the end. Others, maintaining the same symmetry, actually close the thing with a hexagon and may even close the second string with a hexagon, having perhaps a few dendrites pointing out like that. And every snowflake is different from any other snowflake. So now we have there difference and repetition. The repetition of the hexagonal symmetry, but with an added difference. And that's the kind of morphogenesis that we're interested about. The one that includes both difference and repetition. Variety. So it is like a melody that jazz musicians are improvising on and are changing to the point where the original melody is not anymore a kind of pattern to be followed, but the melody is the variation. The melody exists in all its different variations by all the different musicians, and that is what the real melody is, not the original melody you began with. So difference and repetition together produce very interesting types of morphogenesis. What is important here is that they all happen at critical points of intensity. Now those critical points of intensity occur in a variety of contexts. Not only here. There is, for instance, another series which now has to do with what is called manners or regimes of flow. From uniform flow before a certain critical point to periodic or wavy flow to turbulent flow. That is supposed to be an R. Turbulent flow. The way in which any liquid flows depends on its speed. At a speed, of course, being an intensive property. For very small speeds, a liquid flows relatively uniformly. It's kind of a boring type of flow, doesn't change. At a certain critical point of speed, it depends on the viscosity of the flow, so I'm not even going to write numbers like I did over there. It begins flowing in a wavy way. Goes forward and backward, goes forward and backward, or you can even create convection cells that go like this. At another critical point, it becomes turbulent, which now means eddies within eddies or vortices within vortices. That's another architecture, that's another form that has been born from intensive thresholds. This is another type of morphogenesis. Even in animals, we can find this intensive sequences. We can find them in the gaits or manners of moving of animals. I could use myself as an example, but bipeds, we have less gaits. Gaits is the name for this manners of movement than quadrupeds. So let's use a horse as our example. A horse at very small speeds, at very low speeds, can walk. But at a certain critical point of speed, it has to break into a trot. And at another critical point of speed, it has to break into a gallop. You can test this by placing a horse on a conveyor belt that you can manipulate the speed. And then, so that the horse needs to move just to keep himself in the same place, right? So you begin the test by moving the conveyor at a very slow speed, and you can see the horse staying in the same place, walking. Then you get to the critical point, and you can see the horse immediately begin to use different muscles, and even in some cases different bones, in order to be able to now trot, just to keep up with the same speed. And then you start fooling around with the horse's head, right? Like, okay, now I'm going to put you in the turbulent mode, right? And he has to break into a gallop. Now you can check this with yourselves when you are out there. Just try walking faster and faster and faster. There's going to be a point at which you cannot go any faster unless you break into a run. And break into a run means not only using the muscles from your legs, you start using muscles from your back. In other words, a different configuration of your component muscles and bones begin to enter into action when you change into another regime of movement. So critical points of intensity are everywhere. It's just a matter of making a thorough catalog of them to begin finding them in all the different places. But they are also characteristic of intensive thinking. Right? Intensive thinking, therefore, to summarize, is thinking in terms of productive differences, differences that store fuel, and thinking in terms of critical thresholds, the crossing of which produces a spontaneous morphogenetic event. The morphogenesis can be towards a boring form of repetition, or it can be towards a more expressive, more artistic form of repetition. Clearly, as artists, you could use critical thresholds in your art. You can arrange things in your sculptures. You can arrange, particularly now with digital media, you can arrange things in such a way that if a critical mass of the audience is present in front of the monitor, something would happen. If the mass is below critical, something else will happen. And in such a way that you can, if the movement of people is past a certain speed, something would happen. You can begin playing with these critical thresholds to trigger events in the in the materials that you're using for your work of art. All of this is useful for artists But it's also, of course, very useful for scientists and philosophers who are trying to think about the morphogenetic powers of nature. Finally, topological thinking. Now, topological thinking is used by Deleuze mostly to think about all those possibility spaces that we were talking about yesterday. I'm going to repeat a little bit of what I said just to refresh your minds. Yesterday I said that in addition to properties, all those material entities that I claim exist independently of our minds possess, in addition to properties, extensive and intensive, possess capacities and tendencies, right? I used the example of a knife yesterday because it was the most obvious one. A knife can be sharp or not sharp right now, and it's either actually sharp or it's not actually sharp. But its capacity to cut need not be actual. So Deleuze then coins a word, or rather borrows it from Bergson, because that's where the word comes from. Bergson being, of course, a philosopher from the early 20th century who was extremely famous until he got into a debate with Einstein and lost the debate with Einstein. Now, this is my advice. If you're going to get into a debate with somebody, don't get into a debate with Einstein. It's the easiest way of ensuring that you're not going to do very well later on. Bergson had to be resuscitated or revived by Deleuze in a book called Bergsonism, because after the debate with Einstein, he totally lost it. He forgot that speed has critical thresholds. All Einstein was trying to say is, you know, is that famous example of the two twins. Remember the two twins on Earth? They're identical twins. One gets into a spaceship that's going to go at closest speed of light. The other one stays on Earth. The guy that goes at closest speed of light then comes back, and when he comes back, you know, they both were 18-year-olds when the first one departed. When that one comes back, he's only 19, and his other twin is already in his 80s, right? It's like, what happened to you? I mean, I told you to stop smoking. And the reason why is not because there was some kind of miracle happening in the ship, it's because there are critical thresholds of speed. The faster you go in speed, particularly relative to the speed of light, the slower every oscillator begins to pulsate. By oscillators, I mean the atoms out of which the spaceship is made. Remember, every atom has electrons going around at a certain period. So it's oscillating, it's vibrating. Every single cell in your body is vibrating, not necessarily vibrating this way, but it has a metabolic cycle that goes either once or twice or 3 times a day, right? And everything that oscillates or vibrates, there's an intensive effect of speed at which the faster you go, the slower these oscillators begin to vibrate. So the twin that goes in the spaceship begins to oscillate slower. Every single atom begins to vibrate slower. Every single cell begins to have a slower metabolism. So there is an actual objective effect on the aging process due to speed. Right? This is one of those intensive effects that we discovered at the beginning of the 20th century, first theoretically. Today we have proved it, not with twins, of course, nobody has done that, but with the only objects on Earth that go close to the speed of light, particles in a particle accelerator. In a particle accelerator, you have to take into account this slowing down of vibrations when you design the particle accelerator, because they are a true objective effect. So it accounts for the fact that the second twin doesn't age as fast. Bergson didn't believe that. Bergson thought that it was just a subjective effect. His argument was, you know, it's the same thing as when you think about space. When someone is talking to you, and you're talking person to person like this, and then that person goes away, it's just going to seem that it gets smaller in size, right? As it gets farther away, there's an optical effect that seems like it's getting smaller in size, but you never think that the guy is actually shrinking and becoming a midget as he goes away, right? You're expecting that that's just an optical effect. So he said the same thing is with time. The twin in the spaceship doesn't really age any slower. It's just a subjective effect of its being going, really fast, moving away from the Earth. I keep arguing that. He lost the argument, and almost automatically he became unfamous. He had to be revived by Deleuze. But nevertheless, his work is still very valid. He just shouldn't have gotten into that debate, particularly because if you explain it to Bergson correctly, it actually fits with Bergsonian theories. So virtual in Bergson's means real, but not necessarily actual. I suppose you can also call it potential or possible, but we would not want to do that, because when we talk about virtual, we're not talking about just possibilities. We're talking about the structure of a space of possibilities. I gave you yesterday the simplest possible structure for a space of possibilities, the space for a bubble, for a soap bubble, which has a single singularity, a minimum of surface tension. That's the simplest possible possibility space. There's many possibilities. Each point in the space is one possibility, but it then has a singularity. It has a special point, the minimum of surface tension, which acts as an attractor, which is why soap film gets attracted to that point, and by being attracted to that point, ends up being a bubble, right? So, but there are, of course, spaces of possibilities that are much more complex. Today, mathematicians are working on it, but it has always been mathematicians who have been working on this idea. So in order to be able to, if the virtual is that which is real but not actual, and we define the virtual as the structure of a space of possibilities, that is that which gives something that's not actual its reality, then we need mathematics, or we need some form of geometry to think about these spaces, because they are not real spaces, they are abstract spaces. And that geometry is topology. Let me introduce this theme by making a comparison of how things were done in the 19th century and how then things were done when these were invented. I'm going to take a two-dimensional space, which is just a curved piece of paper, right? It's just a two-dimensional space. At the beginning of the 19th century, when you wanted to study a folded two-dimensional space like that, what you would do would be to inscribe it in a space with one more dimension and put some Cartesian coordinates in that space. And then every point, remember that in mathematics, a space is simply a set of points. It's not just a set of points, it's a set of points plus a definition of what counts as a neighborhood. That is, a definition of what counts as one point being nearby another point. Otherwise, a space could be made out of a point in my skin here, then a point in the surface of the moon, then a point in somewhere in Andromeda, then a point in the molten iron center of the Earth, and all those points would form a space. Well, no, they don't, because they don't form neighborhoods. For a space to be coherent, a bunch of points need to be able to be grouped together and then be nearby enough that they actually form a coherent space. So in mathematics, a space is a set of points plus a definition of what is a neighborhood, or a definition of what it is to be nearby another set of points. So prior to, at the beginning of the 19th century, you would take one point of that space, you wanted to identify it, to give it an identity. So what you would do would inscribe that space in a set of Cartesian coordinates and then measure the lengths that it had to those coordinates, and then write those lengths as x1, xy, z, right? This would be the y-axis, this is the x-axis, this is the z-axis. So every point becomes an xyz address, a triple of numbers. In many systems of computer-aided design today, we still use x, y, and z. We still use those axes. We still say, well, if you spin a cube like this, you're spinning it around the z-axis. If you spin it this way, you're spinning around the x-axis. In other words, we still use this. because this is the classical way of doing things. But Deleuze rejects this because he says a space should be studied only with local information that's on the space itself. We don't want to introduce a global set of coordinates relative to which we are studying our space. So, in the 1830s, roughly, two genius mathematicians, one was Gauss, and the other one was Riemann. Riemann was Gauss's disciple, decided to invent an entirely different approach to space. They still wanted to study those folded two-dimensional spaces. In fact, this is what Gauss did. He studied the two-dimensional case, a folded piece of paper like that. But what they wanted to get rid of is this ridiculous Cartesian coordinates. Why do you have to put the space inside a box in order to study it? Why cannot just use the space and study it in itself? But what can we use to do that? Well, what we can use is the differential calculus. I told you about the differential calculus yesterday, and I'm going to repeat my example again just to refresh your memory. We have a corpse with a bullet hole in his head. And what we want to know is at what speed was the bullet going right before it hit the guy in the head. That is, right before it killed him, at that very instant. In other words, what we want to know, because the forensic doctor might be able to use that in order to establish the distance that the killer was from the guy, and therefore to establish whether the guy knew the killer. If the killer was close by, then he might be something that the guy in the corpse knew when he was alive. If he was from far away, it might have been, he might not have even got shot on purpose. He might have been just a casualty of trying to shoot somebody else. So it's important for the forensic doctor to know that. For us, that doesn't really matter. For us, the only thing that matters is that we want to know the instantaneous value of speed at a particular point. So, Gauss knew, of course, this is the 19th century already, the differential calculus is right now the tool of choice for any kind of science. So he knew they had that, and he thought, hey, why can't we use that? Only instead of measuring the instantaneous value of speed, or the instantaneous value of temperature, or the instantaneous value of pressure, let's measure the instantaneous value of curvature at each point. Now let me just give you something like that, but in cross-section so that you understand better what I'm talking about. Let's imagine that we had a piece of paper that's folded that way, and of course I'm just doing it in cross-section, right? The paper goes in that direction here. Well, as you can see here, because this is flat, curvature is not changing at all. So the value for instantaneous change of curvature is 0 here. 0, 0, 0, then begins curving and gets more rapid, so the values keep changing at each one of those points. Then it starts slowing down because now it's going to change curvature at a much slower pace. So, but each one is still changing curvature at a certain speed. You can calculate it. You get here, then it is a more tighter curve, so it needs to accelerate, and then it goes back to 0 again. So you can measure the change of curvature. Remember what I told you yesterday about rates of change. We hear the word rates of change, and it sounds like something that an economist would use, or a physicist would use, and it sounds boring immediately. So change that word to speeds of becoming, and all of a sudden start sounding differently. Becomings can occur at all kinds of speeds, and the speeds at which things become are important. Everything around us is changing constantly, but some things are changing very slowly, some things are changing very fast. Things that change super fast, we don't even see them. We need to take stop motion photography to be able to see them, right? So that clouds moving by themselves. You look at the clouds and yes, you can see that they are moving, but they're moving so slowly that you really need a lot of imagination to see that. But if you take one frame every hour, you're going to see those clouds moving in dramatic forms, right? So they are moving. There's a rate of change, but it's a rate of change that relative to us, relative to our perceptual rate of velocities, is just too slow to be seen. We can use a particular piece of technological apparatus to accelerate them. And then you see the drama of how clouds move. This is why fast motion shots of clouds almost inevitably look more dramatic than just clouds being seen by themselves. Other things change too slow. Well, I mean, sticking to this too slowly thing. A flower blooming. We almost never see a flower blooming. We see the pre-bloom button at night, then we go to sleep, we wake up the following morning, and there's the flower already bloomed. You almost never see it going through its motion, unless, of course, somebody does some stop-motion photography, right? Which is perhaps the very first shots everyone ever saw of stop-motion, those flowers blooming, right? That's a morphogenetic process. But it's a morphogenetic process that is a becoming, the becoming flower of the bloom, but it's a becoming that is too slow for us to be part of our phenomenology. We can make it into a phenomenon by shooting one frame every hour and then playing the frames 24 frames per second. And you see all those flowers blooming, and it looks fantastic. You have made visible a becoming that was too slow for us to see. An even more extreme case is folded mountain ranges like the Himalayas or the Rocky Mountains. Folded mountain ranges like the Himalayas are basically the product of a clash between tectonic plates. In the case of the Himalayas, the tectonic plate on which India is embedded versus the tectonic plate on which Central Asia is embedded. Because of the lava flows that self-organize underneath them and that become a kind of self-organized conveyor belt of lava, they are moving against one another and they're clashing. And when they clash, the lithosphere, the very thin layer of rock on top of which we live and we call our land, begins folding, just like that, right? And as they fold, they rise, and that fold is what the Himalayas are. All the Himalayas are as beings is a folded lithosphere, folded by the clash of tectonic plates. However, if you use lasers to measure very accurately the heights of the different parts of the Tibetan plateau, you can realize, as has been realized by scientists lately, that certain parts of the Tibetan plateau are still going up 1 millimeter a year. Now that clearly is way slower than the flower blooming or way slower than the clouds moving around. Nobody will ever be able to see that. You need laser interferometry to detect it. Also, moving up 1 millimeter a year doesn't have any consequences for us. You know, Mao's armies, when they invaded Tibet, it's not as if the general went, Generalissimo Mao, you know, but the mountains will be 1 millimeter higher next year. We need to invade today. 1 millimeter, I think we can handle that. So it doesn't have any practical consequence, but it has a philosophical consequence. We look at the Himalayas as the perfect example of a finished being. A being that has been there forever and that will be there forever. You point it to your kids and saying, see, your grandpa and the grandpa of your grandpa and the grandpa of the grandpa of your grandpa saw those mountains where they were, and your grandsons and the grandsons of your grandsons will see that mountain. But if those mountains are still going up 1 millimeter a year, it means that they are still being folded. And if their being consists in being folded, that means that they are still becoming what they are. In other words, everything is a becoming. There really are no beings out there, except that very slow becomings to faster becomings like ourselves seem like beings, and we can treat them as beings for all practical purposes. Mao's army can cross the Himalayas even though they will be 1 millimeter higher next year. It doesn't make any practical difference for us. It doesn't make any perceptual difference for us. But if you use laser interferometry, you can bring that phenomena into our consciousness because they are still going up. They're still becoming what they are. Right? So speed matters because the speeds of becoming is what gives apparent stability to things around us. The same thing happens, by the way, with very fast becomings, like the bullet that we were just talking about. If someone in front of you gets hit by a bullet, all you're going to see is that the guy was talking 1 second, yeah, no, but I like this you're this quarterback better than, and all of a sudden he's dead, right? You don't see anything. But if you shoot that guy, not with stop motion, but with the opposite, now 700 frames per second or 1,000 frames per second, and you then play him back at 24 frames per second, you're going to see that bullet slowly going. You're going to see the opening of the wound. You're going to see the becoming wound of the wound, the flowering of the flesh. You're going to see the blood splashing, right? You're going to see pieces of brain kind of coming out. And I'm not going to go on and on and on because I'm grossing you out. And then you're going to see the guy slowly dying. You see the event, an event that is invisible at our regular speeds. So we can use technology to transform invisible phenomena, invisible events, either because they are too fast or either because they are too slow, to translate them at our speed and bring them to our speed so that we can actually see, oh wow, yeah, that's the becoming wound of the wound, and that is the becoming cloud of the cloud. So speeds matter. And having the differential calculus matters too, because it's a piece of mathematics that works with speeds of becoming. So, going back to mathematics. Gauss and Riemann thought, do we really need this awful thing over here, this extra space, this transcendent space, this global space from which we can determine the identity of the points? Or can we determine the identity of the points exclusively by their instantaneous speed of curvature, by the instantaneous rate of change of curvature at that point? By doing that, every point in this plane becomes a speed, and the entire space becomes a field of rapidities and slownesses. The rapidity or slowness with which curvature is changing at every point. And by reconceiving space that way, Gauss and Riemann completely revolutionized geometry, because they went from a geometry that was extensive to a geometry that was intensive. Now, this was done by Gauss in the 1930s. He solved the two-dimensional case. He passed the baton to his disciple, Riemann, who was expected, as any disciple, to just do the next case, to solve the three-dimensional case. Right? But Riemann was cocky. Riemann just went for the whole enchilada. And he solved not only the three-dimensional case, but the n-dimensional case, that is, spaces of any number of dimensions. Now, an n-dimensional space that is intensive, that is a field of rapidities and slownesses, is called a multiplicity or a manifold. That's the mathematical term. And Deleuze adopts the word multiplicity from there. Deleuze loved this because it got rid of the transcendent global set of coordinates. But that's just the philosophical consequence. There was an even more direct scientific consequence. This was done in the 1840s. As with most discoveries in mathematics, they lay fallow, in the sense that mathematicians know about it, but nobody else knows about it. Physicists didn't know about it until Einstein. Einstein, at the beginning of the 20th century, took some classes, or there were more kind of chats with an expert on geometry who told him about this. He was fascinated by it because he thought, boy, this could be applied to real space. This is not just about mathematics. In Newtonian science, the Newtonian version of the universe, every planet had an X, Y, and Z address. In his imagination, of course. And Newton believed that there was a set of Cartesian coordinates somewhere out there. Those were called absolute space. Of course, those Cartesian coordinates, I don't know exactly how he imagined them. It's sort of like, today we kind of laugh about it. It's sort of like thinking of the North Pole as having a, candy striped, pole or something. And you get, oh yeah, we're finally at the North Pole. So I don't know if he thought that if you took a spaceship and you try to find it, you would actually find the Cartesian coordinate, to the left, to the Cartesian coordinates. Okay, let's go there, Mr. Spock, take a left. Einstein realized, hey, wait a minute, it is impossible that we will ever find a set of Cartesian coordinates out there giving us the absolute reference for all the ascriptions of space position for all the different planets. That's what his theory was called relativity. He got rid of absolute space, and he said, let's use Gauss and Riemann's geometry for the universe. Gauss and Riemann geometry works exclusively with local information, how the curvature is changing at each one of these points. Now let me change pages so I can show you what Einstein did. Einstein began to think about real space, about outer space, in these terms. Real space can be curved, and what curves it or fails to curve it is the amount of gravity of objects around it. In other words, space is not just a container, like a box, where you put planets and you put stars. Space is shaped by its very contents. So huge stars will bend space more, smaller stars will bend space less, and space is really this folded, three-dimensional entity. And to prove it, he said, well, let's think about this. Let's take Earth. Again, Earth identified by Mexico. What other country could we possibly use for that, right? Let's put some islands here just to be fun. And let's say that the sun is over here. Now he took two stars that astronomers had seen for the longest time, and astronomers knew that there's a certain distance between the stars, let's call it x, that you could, particularly when you see them at night, you could see the two stars, and then you could measure with an astrolabe or using some astronomical instrument, you can measure the distance between the two, and astronomers for a couple of centuries were sure that that distance was x. Right? Einstein, though, said, well, yes, I accept that, but when those stars are behind the sun during the day, the rays of light that they send to Earth will be curved, because the space around the sun will in fact be curved a little bit. And so these guys will get around the sun will curve a little, and then they will go like that again, instead of being one straight line, like they are at night. At night they reach us in a straight line. But during the day, they reach us following this kind of curvy line. So he figured, if you are here and you take a photograph of those two stars at night and you measure the distance, they're going to give you, say, 10 centimeters. But if you take that photograph during the day, they should be 10.5 centimeters apart. Of course, you couldn't test that idea because during the day you don't see the stars. The sun is blocking the stars. So he put out that idea in 1905, and he had to wait 14 years until 1919, where there was a total solar eclipse. The moon was going to go in front of the sun, was going to block the sun completely, and was going to let us see those two stars without the interfering light of the sun. Astronomers knew exactly when the date was going to be, so every scientific society, the Royal Academy of London, the Royal Academy of Paris, and all the famous scientific societies, put a lot of money to send scientists to all the different places. I can't remember now where was the optimal place to see it. I think it was somewhere in New Zealand. The optimal place where the eclipse were going to be seen. Everybody sent expeditions of scientists armed with photographic cameras to take a photograph of those two stars the moment the sun was blocked, to see if in fact the distance between the two was going to be 10.5. When they developed the photographs and measured the distance, it was 10.5, and at that very second, Einstein became a superstar. Right? His theory had been confirmed, the special theory of relativity. Space did not have an absolute set of coordinates from which we could measure things. Space could only be treated locally by measuring curvature and the rate at which it curves. But Einstein would not have been able to do that had it not been for Gauss and Riemann. So let's remember, you know, their theories lay fallow there for 70 years, but eventually they were applied to real space, and they made a scientist into a superstar. Now, for our purposes here, these kinds of spaces are interesting. I mean, these ideas are interesting, but we don't want to apply topological thinking to real space. We want to apply it to those conceptual spaces that we've been talking about before. The conceptual space associated with a knife, which tells you all the possibilities that the knife can do. The conceptual space associated with the bubble, the soap bubble, all the possibilities that the soap bubble can have. In other words, we want those spaces to be used conceptually, philosophically. The person who invented that use for those spaces, I mentioned him earlier. His name is Henri Poincaré. That name has an accent somewhere. I don't know where it is. Boy, we have 20 minutes. Okay, Henri Poincaré. Henri Poincaré, as I said yesterday, was one of the greatest mathematicians of the late 19th century, early 20th century. In fact, he is co-credited with the theory of relativity with Einstein. Einstein is the famous one, but Poincaré had already thought this idea before Einstein. It's just that they did not communicate. Einstein at that time was very young. He was working as a clerk for a patent office, so he was the opposite of famous. Poincaré was super famous, was much older, and he had already worked for the French government and had positions in all kinds of ministries and so on. He was friends with politicians, he was friends with generals. And so they both invented the theory of relativity separately. But Poincaré invented something else. He invented spaces of possibilities. He said, if we need to think about the virtual, that is something that is real, but it's not actual, then we're going to need to think about how those possibilities are structured. We need to think about in terms of singularities. So he invented a notion which he called phase space. And I'm going to also draw it the way I drew my other ones, even though actually these spaces are not used in mathematics because they have edges. What you do in mathematics when you want to use a two-dimensional space like that is you glue first that edge to this edge. You create a taco. Right? You first glue those two edges, and then you glue this edge to that edge, so you end up with a torus. You end up with a donut. That way you eliminate the edges. Because the edges is almost like when people thought that the earth was flat and had an edge, and the ships were all going to fall out into space. Edges introduce artifacts. And so you normally get rid of those edges by doing that. Now, I'm not going to be able to be drawing toruses all the time, so I'm just going to be drawing my simple drawing over here. So first, he began studying soap bubbles, crystals, and things like that, and found out that all of them had a simple singularity, which he called an attractor. He called it an attractor because, well, okay, let me explain this a little better. Let me explain, first of all, how you create phase space. Number one, phase space, by the way, is a way to study the possibilities open to a dynamical system. It can be a soap bubble, it can be a pendulum, it can be a steam engine, it can be a thunderstorm, it can be anything that's dynamic. Right? So the very first thing you need to do is identify the relevant ways of changing. Here comes that word again, change. If we're going to be using rates of change, we need things that change of a system. Let me draw a very, very simple system down here. A pendulum. You know, like in a grandfather's clock. A pendulum is hinged up here. It has the thing over there. Now let's assume that this is not a driven pendulum, like in a grandfather's clock. In a grandfather's clock, Something has to be given a little pulse to the pendulum so it keeps going, otherwise the pendulum would come to a halt. Assume that this is not a motorized pendulum, it's simply a thing with a weight hanging from a hinge that allows it to spin. Right? Now this pendulum is a dynamical system, it can change, but it can change in only two ways. Let's assume that I take this and move it up here, and then I let it go. It will swing, and then the swings will become smaller and smaller and smaller until it goes back to its equilibrium position, right? So it can change in two different ways. It can change in position. I can put it in this position, I can put it in this position, and it can change in speed. Right? When I bring it up here, it's at 0 speed, but as I let it go, it begins increasing in speed. It reaches its maximum speed when it's down there, then it starts slowing down. It gets still it comes to a still here, and it goes back, reaches its maximum speed again, and then it begins swinging, 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 swinging until it becomes motionless again. So there's two ways in which the pendulum can change: position and velocity. But you can say, but hey, wait a minute, the pendulum can change in many, many other ways. I can take some day-glow green paint and spray some graffiti on it. That'll be a change, right? It'll be different than the original pendulum. I can also stick glue a stick of dynamite and blow up the pendulum. Hey, that's gonna be a change. Just ask the pendulum after it blows up. But those would be irrelevant ways of changing. We want only the relevant ways of changing. They are irrelevant because the TNT, first of all, creates a new system, which is not a pendulum by itself. It's the pendulum plus explosive. So now you're not dealing with the same thing. The color doesn't change the dynamics of the pendulum. Now, let me just say something about the word relevant. Assessments of significance or relevance, what factors are significant or relevant for a given thing, is an art. It's not a science. You don't have an algorithm, a mechanical recipe that will be able to identify what makes a difference and what doesn't make a difference to the dynamics of the pendulum, right? You need to experimentally set that. You can change the pressure, you can change the temperature, and you see that the speed is still the same. Well, so temperature doesn't change it. Or temperature might change it a little bit, and for your experiment, that is too small an effect to be counted. So making assessments of relevance is an art. It's the kind of art that you need to learn. We're going to talk a little bit more about that tonight when I distinguish two types of knowledge. Knowing that Columbus discovered America in 1492, or knowing that the hydrogen atom has only one proton in its nucleus. Knowing facts, from knowing how to swim, knowing how to ride a bicycle, knowing how to paint, knowing how to play an instrument, knowing how to, knowing how is skills, is embodied knowledge. It's entirely different than knowing that. Knowing that someone tells you Columbus discovered America in 1492, if you believe him, then you know that Columbus discovered America in 1492. But knowing how, is taught by example and is learned by doing. You don't teach your kid to learn the bicycle by reading an Acme volume on how to ride a bicycle and then throwing your kid downhill. Good luck, kid, right? You climb the bicycle yourself, you teach them by example, see this is how it's done, and then the kid learns how to ride a bicycle by doing, over and by practicing. Right? Knowing how, I'm going to talk a little bit more about that tonight, has been neglected by philosophers, has been systematically neglected by philosophers who are too elitist to consider working with your hands, as in a craft, as in metallurgy or carpentry or pottery or cooking, a significant form of knowledge. But we have to get past that prejudice, because knowing how, as I'm going to argue tonight, is 1,000,000 times harder to reproduce in robotics than knowing that. It's so much easier to create a computer that pretends to talk and to understand sentences and pass the Turing test by pretending to be human, than to create a computer that you can teach it how to swim, that you can teach it how to ride a bicycle, that you can teach it how to play the piano, that you can teach it all the things that you can teach a human being. Knowing how is the hard part. But because knowing how is typically done by artisans, not by elite scientists, is disregarded by philosophers. The only philosopher that has not done that is a philosopher called Gilbert Ryle. I'm going to write his name when we come back tonight, because this is going to become crucial tonight. Spotting relevant ways of changing is know-how. It doesn't come in books, right? There are no set of principles that will tell you this is how you spot significant changes. You know, knowing what makes a difference for a particular dynamical system, you learn by experience, by repeated experience, and you're taught by example during your apprenticeship in a laboratory. So, the first thing that you need to do then is to rule out spray paint, is to rule out the color of the pendulum, to rule out you know, if it's wood, the particular grain of wood that it is made out of, by not adding irrelevant things like a stick of dynamite. And then you boil it down to, well, the two main ways of changing is position and velocity. These are called the degrees of freedom of the system, technically. That is, the ways in which the system is free to change. Free, done. I cannot talk and write at the same time, apparently. Number two, create the space, create a manifold. I'm going to write there now the technical term. Remember, a manifold is just a space that is used in the way in which Riemann and Gauss used them, with as many dimensions as you need. With as many dimensions as degrees of freedom. So for a pendulum that has 2 degrees of freedom, you need a 2-dimensional space. Finally, number 3. A state of the system is a point in this space, a series of states equals a trajectory, or a series of points in that space. So what Poincaré then did is giving us a way of thinking about the space of possibilities, in this particular case of the pendulum, or the space of possibilities of anything, as long as you can identify the relevant ways of changing. Now I'm going to switch to another page, right, to draw the pendulum. So, we located the degrees of freedom of the pendulum, speed and position. We're going to assign those to each one of the dimensions of our manifold. This is position. Remember now, the dimensions are in the manifold itself. They are not in some Cartesian coordinates outside. This dimension is position. This dimension is velocity. So the pendulum, I'm going to redraw it here in small scale so that we can see it. At any one point, you know, if I move it up here and keep it motionless, I change its position, and its velocity now is 0 because I'm holding it. So that has, you know, say that this is 0 velocity, and this is also graduated for position. We calculate its position, we calculate velocity, it has a point right there. That is, any one particular state of the system becomes a point in phase space. Now, for a two-dimensional entity like a pendulum, this becomes almost obvious. But think of something like a bicycle. A bicycle can change in at least 6 or 7 different ways. Each one of the 2 wheels can rotate. That's 2 ways of changing. Then there is the handle that can rotate in a different way. That's 3 degrees of freedom. Then there is the pedals that can rotate also independently, particularly when they are disengaged from the chain. Then there is the connection of the change to the pedals to the following thing. When you measure all the different ways in which a bicycle can change, you end up with 6 relevant ways of changing. Again, disregarding the color of the bicycle, disregarding the height of the bicycle, disregarding all kinds of things that are irrelevant for studying the dynamics of a bicycle. So a bicycle would have a 6-dimensional space. We cannot draw a 6-dimensional space, but mathematicians can handle spaces with as many as infinite number of dimensions. In quantum mechanics, what is called Hilbert space has an infinite number of dimensions, and mathematicians can handle that with no problem. So, but because we want to draw these things, let's stick to that. The point of the example of the bicycle is that a particular state of the bicycle, with the wheels rotated just so, the handle rotated just so, and everything in just so position, would also become a single point in that 6-dimensional space. So you're trading the complexity of the object for the complexity of the number of dimensions. But any object whatsoever at a particular point in time can be reduced to a point in that space. Now, as the pendulum swings, or as the bicycle moves and its wheels spin, the point will change, and as I said here, a series of states, right? A series of states becomes a trajectory. And so you will here. It will be a series of points, different states, and if you join them together, there will be a trajectory. So a particular history of the bicycle, a particular history of the pendulum, that is a particular episode in its life, becomes now a trajectory in phase space. So far, so good. So far, it's just a representational device. So far, it's just a way of making visual something that was more embodied and slightly more complex to understand. If that's all Poincaré had done, this would not be a big deal. Let me just draw another, because it's the same space with position and velocity. Now, what would this pendulum look like if I move it up here and not let it go? Right? It's going to have its widest swing, then every swing will be less wide than the one before. Swing, 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 until it comes to a rest. Right? In phase space, that would look like that. The wider swing would be like this. Then a smaller swing, then a smaller swing, then a smaller swing, until it comes to a rest. Right? We are assuming that this is 0 velocity. And these are different positions for the pendulum. So you have, Poincaré then allowed us to visualize dynamical things, becomings, as trajectories in a space, which was a very interesting thing. We want to deal with becomings, we need instruments. We need representational technology to be able to better understand those becomings, better understand those dynamics. If that had been it, though, then this would have been just a representational revolution. It would be one more type of modeling technique used by scientists, in which they're using visual models to be able to better understand dynamical behavior. But that's not what he found. He began to explore this thing. He began first to use very simple systems that are similar to the crystals and the soap bubbles that we saw before. Right? And I can't remember right now what his system, but it was something that he could manipulate the starting point and then see where it goes, where it tends to go. So he began with his system at a particular state, somewhere over there, and then began following his system as it created a trajectory until it came to a rest. Then he took the same system and started in a completely different place, say over here, followed his trajectory, which now followed a very different trajectory, and ended up in the same point. He goes, oh, well, that's interesting. Then he began it in a completely different place. He began wandering around and ended up in the same point. And so with every trajectory that he tried. Then he realized that that point was a singularity, was an attractor. Every trajectory, doesn't matter where it began, ended up there. And he realized at that instant that what he had discovered is a way of representing the tendency of a system to always end up in the same place. This map is the map of the soap bubble. But it's also the map of the cubic crystal, or any other crystal, or any other thing that minimizes something. A soap bubble will be created, you blow in a certain way and it blows differently and it becomes a sphere following one trajectory, but eventually ends up in the point of minimum tension. Then you blow the soap bubble in a different way, blowing from the side. Well, that means that you're starting the soap bubble in a different place. It goes through its convolutions until it ends up as a sphere and ends up in that place. So Poincaré realized immediately that he had discovered a way not only of representing tendencies. Remember, tendencies are real but not actual, right? Because that film of soap in the wire is potentially a sphere, but it is not a sphere right now. Right now it's a flat thing. It will become a sphere if I blow on it. It becomes a sphere. So that sphere is potentially there, it's virtually there, but it's not there yet. So Poincaré realized immediately when he began discovering this was around the turn of the century, that he for the first time had found a way of capturing graphically what tendencies are. He realized that he had found a way of representing mathematically the virtual, the simplest type of virtuality, which is an optimization process or a minimization process, but many things do that. We know that when Katrina hit New Orleans and the Mississippi overflowed, it flooded the city, we knew that poor people living in the lowest elevation neighborhoods were the ones who were going to get hit worse. Why? Because water always seeks the lowest level. Right? We use that sentence, right? Water seeks the lowest level. Now, water doesn't seek anything in the sense of actually finding something. It's rather, water has a tendency to go to the minimum point of gravity, that is to the lowest point. And so we knew when Katrina hit that the lowest point of gravity was the poor neighborhoods. Rich people live in the high points. So that tendency of water to seeking the lowest level is another thing that is represented by this diagram. That is the lowest level, the lowest intensity of gravity. Right? So Poincaré discovered then this and called these guys attractors. Topological points that could become spheres, that could become cubes, that could become all kinds of different forms once they become actual. But the diagram itself was simply a way of capturing the structure of a space of possibilities. This was a space of possible states. That's what phase space is. It's a space of possible states, given the relevant factors, of course, right? Given that we have already narrowed down what makes a difference and what doesn't make a difference. Every single point in this space is a possibility. But we don't care about all of those possibilities. If every trajectory is going to end up over there, well, then the only thing that we should care about is that guy, right? And that facilitates our thought about these spaces, because now we just have to concentrate on the structure of the possibility space, not on all the possibilities, which can be infinite. Perhaps not for the soap bubble, but for many other things. Let me give you just a very simple example. Everybody knows that proteins and enzymes in our body, which are necessary for digestion, necessary for respiration and so on, are long chains of amino acids. We talked about that yesterday when we talked about spider silk. An amino acid is a molecule, but we can consider it a single atom if you want to for this example. They are just chained together. Now, proteins draw from a repertoire of 20 amino acids. That is an entirely arbitrary number because there are more than 100 amino acids. Why life decided to use an alphabet of 20 letters, who knows? But that's what it is, right? So, mathematically, the way you measure, you have, for instance, a protein that's 10 amino acids long, and you want to know how many combinations can be formed if you start permutating or changing around the amino acids? Well, mathematically it's very easy to calculate that. It's the number of elements that you're using, 20 amino acids in this case, raised to the length of the chain, in this case 10. Right now this is what, something like 20 million or something, but I can't right now do the math, but it's a long number. But now think about that. In other words, that's the space of possibilities for that protein, because all the possible combinations that it could exist in, right? Now, the smallest enzyme in our organism, not even hemoglobin or something like that, that's much more complicated. Even a very humble, tiny enzyme is about 300 bases long, which means that it's 20 raised to 300. Now, when you put that in your calculator, you can do it right now if you want to, put 20, raise it to 30, and your calculator is going to respond infinity. It doesn't even get that far. And that is the smallest enzyme in an organism, right? Now imagine something like hemoglobin or the enzymes that we use for digestion, which are 1,000 amino acids long. Well, the space of possible combinations is an infinity of infinities, right? So that goes to show you how important it is to be able to disregard all the possibilities and concentrate only on the structure, because most possibility spaces are infinite that way. And if we could not handle all that infinity of possibilities. But if we can find that certain parts of the space are privileged, that those parts of the space have the highest probability of becoming actual, then we have found tendencies. And then we have found a mathematical way of dealing with tendencies. Poincaré continued, oops, guys, we are already eating into lunchtime, so I'm about to end. Poincaré continued his research and discovered a new type of singularity, which I already explained yesterday. It's a line singularity that's closed on itself. It's called a limit cycle or a periodic singularity, a periodic attractor. And it does the same thing. Trajectories can begin anywhere, but the moment they reach the singularity, they wrap around it. They can begin over here, and they wrap around it. They can be here over here, and they wrap around it. In other words, a singularity is the long-term tendencies of the system. The system can start wherever, but you know that in the end, after you wait 5 minutes, 10 minutes, 20 minutes, it will start pulsating. I gave you as an example yesterday, and I'm drawing it ever worse, a radio transmitter. A radio transmitter, when you turn it on, it begins acting erratically, something like when your cell phone is trying to find a signal, and the erratic behavior is precisely this trajectory over here. Engineers call those transients. You know, it's what happens to a radio when it's warming up. But eventually, it settles into a steady pulsation. I already explained to you what happens yesterday. Spherical waves of electromagnetic energy get put out, and that is the signal on top of which you can then piggyback a message. Right? Poincaré also discovered those. Today we already know, and this I told you yesterday, I hope that some of you actually followed my advice and Googled Lorentz attractor. You know, when I tell you guys that something is cool, something is cool. I just wanted you to see it for yourself, because chaotic attractors are intriguing aesthetically. You know, they are very interesting visually. They look different than anything else that you've seen before. But at the same time, they are abstract entities structuring possibility spaces. I mean, I'm going to have to stop, but let me just then give some kind of punchline or something. Poincaré then invented topological thinking. Topological thinking, according to Poincaré, then is this. Is thinking visually or geometrically, if you want to put it that way, about the virtual. It's thinking in terms of, if we have tendencies and capacities, both of which are real, but not necessarily actual, how do we think about them when they are not being actual? How do we think about the knife when it's not actually cutting something? How do we think about the soap film when it's not actually a soap bubble? Well, that's just a possibility for it. But it's not as if it had any, it's not as if the possibilities didn't have any structure, as if that piece of film could become anything. No. It has becomings, but the becomings are narrowed to a certain class, right? And that's what we want to understand. What is the structure of the possible becomings for a system? Do they have structure? And topological thinking allows us to do that, okay? Now, tomorrow, or rather on Tuesday, when we get back to science, because I'm going to stop with, I know, well, we'll have a little bit of science tonight, but I'm going to go back. Tomorrow we're going to talk about history and economics and society. I'm not going to be talking about physics or biology, but we'll return to this. I'm going to try to show you how the three reasoning styles together weave beautifully into a worldview in which, first of all, you always think in terms of collectivities, populations, in which the variation is essential. Not only populations that reproduce themselves, but also, as I was saying yesterday, populations of atoms, populations of molecules, populations of anything, in which what you are interested in is in the variation in the population. Number two, thinking always in terms of where is this process getting its fuel? Where is the morphogenetic process that's shaping this population, where is it, what is it being fueled by? Well, intensive differences, intensities is always going to be one answer to that question of what's governing that process, what's driving that process. And then when you ask yourself, well, yes, but where is that process going? Do we have any idea what its future is? We know it's becoming, and it's becoming because it's being driven by intensive differences, but do we have any idea where it's going? Well, yeah, we can map its space of possibilities. If its space of possibilities has only one attractor, then we know exactly where it's going. We know that this is going to end up as a sphere. But spaces of possibilities don't have to be like that. There are many spaces of possibilities that are like this, for instance. With many attractors, and each attractor with its own sphere of influence called its basin of attraction. I suppose that is a metaphor having to do with the basin of a river. A basin of a river is its catchment area. You know, the raindrops that it attracts as they fall down the hills and end up in the river. That's the metaphor. But, you know, this, for instance, could represent a fertilized egg. Imagine a fertilized egg of a chicken, a fertilized egg of any kind of animal. At the beginning, where it is just a single pluripotent cell that eventually could become bone cells, could become muscle cells, could become feathers, could become beak, could become eye, right? And it has all these attractors, which are eye, feathers, and so on, of the dynamics of the internal DNA of each one of the cells. As the pluripotent cell begins to unfold into a chicken, right? Each one of those cells begins committing itself to feather. Another one commits itself to bone. Another one commits itself to muscle. Another one commits itself to... So the space starts losing attractors. But a pluripotent cell, and this is why everybody is fighting over stem cell research, because stem cells are like that. The space of possibilities of a stem cell has... You know, we have about 200 different cells, from blood cells, nerve cells, muscle cells, bone cells, kidney cells, cardiac cells, and so on, neurons. And about 200, that means that a fertilized human egg, you know, one cell, the space of possibilities has 200 attractors, one for each of the possible destinies. So you cannot tell, whereas with this one you can tell in advance where it's going, because it has only one. With this one you cannot tell in advance where it's going. Okay? But Poincaré had already discovered that 100 years ago. It's just that mathematical discoveries take forever to get to us. Gauss and Riemann took 70 years to get to Einstein. Poincaré's discoveries are taking about 80 years to get to us. And it was thanks to Deleuze that this process was accelerated, because he weaved all these strands together and gave them to us in the form of a world.